Hey there, Calc 2 folks, back here with another quick video in our study of the calculus of polar curves and equations here. In this video, we are going to look at the case for the area bounded by polar curves. All right. We are going to look at how to calculate that area that's found trapped within polar curves and within what in between polar curves, right? So this formulation that we are going to develop, to begin with, we take note that it does develop from some fundamental calculation, right? And this going back to a calculation you may have learned in trigonometry, or hopefully have learned in trigonometry, known as the area of a sector calculation, right? And what is a sector? A sector is a portion of a circle. That if we would slice a circle into sections so that they maybe form these pieces of a pie, for instance, that piece of the pie is known as a sector in a sense. And how do we find the area of those sectors? Right? Well, this fundamental understanding for calculating the area of a sector is going to be what we use to develop our calculation for the area trapped within polar curves. All right? So what we begin with is recalling that idea from trigonometry. Right? Recall from trigonometry, right? If a sector of a circle has angle measurement theta, right, and radius measurement r, right, where we might note this illustration seen here. Note this is forming, we're looking at a portion of a circle here, where we're interested in this sector here that forms, this region of space that forms over this angle that measures theta in radians, right? If the sector of a circle has angle measurement theta, let's clarify radians, and radius measurement r, right? Notice here this circle does have a radius of r highlighted along the x and y coordinate planes, or axes in the coordinate plane here, right? The distance from the center out to this edge of the circle being r units in length, that area, right, is equal to 1/2 times the radius squared times the value of theta. Right? Theta being this angle measurement in radians, r being this distance from the center of the circle to the edge of the circle, where we're interested in calculating the area of the sector. All right? This formula for area of the sector can be used to develop what we call the formula for the area of a polar rectangle. All right? This formula can be used to develop a formula for the area of a polar rectangle. Now, what is a polar rectangle? Right? A polar rectangle forms in two-dimensional space, right? Within, if I blow up this picture a little bit here, we'll see it, right? It forms in two-dimensional space within, right, this region of space, trapped between two circles of radius r1 and r2, right, where r1 is less than r2 over values of theta in some interval of theta from alpha to beta. Right? If we consider this description in our two-dimensional space, what it defines is this highlighted region seen here, right? This shaded region seen here in this illustration, trapped between these two circles of radius r1 and r2 over these angle measurements of theta from alpha to beta. And what it defines is this space known as a polar rectangle, right? It's not a classical Cartesian rectangle, right? A rectangle that might occur in the xy coordinate plane, but it is a rectangular shape here that lays itself out in the polar coordinate system and within the polar context. All right? Now, if we think about using the formula for the area of a sector here, we will notice that the area of this polar rectangle is really just the area of the larger sector minus the area of the smaller sector. And if we set up that difference of two areas, right? That difference of the area seen in the larger sector, which would be 1/2 r squared times the size of that angle measurement, theta. And there it's going to be the size of our angle is going to go from alpha to beta, so we calculated that as beta minus alpha in size. Right? That's going to give us this angle measurement where if we ignore this portion here, right, we can see that is just going to be our description of area of the bigger section of, all right, the bigger area sector. And then what we do is subtract away this portion here, where this portion here, right, is the area found in the smaller sector, right? The sector here that is not highlighted at all, right? That the sector that exists in this small little piece of the pie right here within the circle of radius R1. Right? When we take the difference of those two sectors, area, we will get the area of this polar rectangle. Right? And that fundamental calculation for area of the sector, and more specifically, this formulation here for the area of a polar rectangle, is what's going to be used fundamentally in our calculation for the area trapped within polar curves. Right? Now, before we head in that direction, let's consider a quick example of calculating the area of a polar rectangle. All right? Here's the case of the polar rectangle trapped between two circles, one of radius 1, so that's this circle here, and the second of radius 2, that being this circle here, over angle measurements of theta in this interval, where this interval starts to form at theta equal to pi over 6, this location here as an angle measurement, forming the side of that polar rectangle, and continuing all the way up until we get to this angle measurement here. That angle measurement there being that angle measurement pi over 3 in value. All right? The area trapped within these two circles in our polar coordinate system over values of angle theta from pi over 6 to pi over 3 in the polar coordinate system, right, has the following calculation, right? And it defines this polar rectangle. If we put this information into our calculation, right, it is going to be 1/2 times our larger radius, that being 2 squared, minus our smaller radius, that being 1 squared, all times by the difference of our two angle measurements, beta minus alpha in value, beta being pi over 3, alpha being pi over 6 in value. Now, pi over 3 with a common denominator of 6 is 2 pi over 6. So 2 pi over 6 minus pi over 6 equates to pi over 6 in size. All right? And 2 squared is 4, 1 squared is 1, so 4 minus 1 results in 3. So it's 1/2 times 3 times pi over 6, which will simplify to pi over 4 units squared. Right? The area found within this polar rectangle is pi over 4 units squared. All right? Now, this is the area of polar rectangles, folks. And as I said, these are a bit more of a fundamental calculation. Let's consider generalizing a little further. Now let's assume that the polar region we're looking at is not rectangular in shape. All right? Where in this case we might consider it forming between two polar curves, two separate polar curves, not necessarily circular in behavior, right? That being the polar curve r equals f of theta, and that being the curve r equals g of theta, where what's unique about g and theta's relationship is that g of theta is always smaller than or equal to f of theta. All right? And let's assume that this polar region is forming between these two polar curves over values of theta in some angle measurement from alpha to beta. Right? This generic description of a polar region is what we see illustrated down here below. Right? This is a region that is forming over an angle measurement from alpha to beta, right? It is forming over these angles that start here at theta equal to alpha and continue up to this angle measurement where theta equals beta, right? Where it's also happening between these two polar functions, right? The polar function r equals f of theta and the polar function r equals g of theta, where we can see here r equals f of theta is this function forming this edge or side of this polar region, which is, we note, further from the origin when compared to g of theta. G of theta being this radial measurements description, where g of theta is this radial description in terms of theta that is closer to the origin. It is this polar curve seen here. So what we're interested in is the region of space trapped between this curve and this polar curve over angle measurements of theta equal to alpha up to theta equal to beta. And it defines this polar region, a region that is not necessarily a polar rectangle, but what is just a polar region trapped between two polar curves. Right? Now in this case, the area of that polar region is going to be given by the following formula. And if we bring this formula into view, we will notice, first things first, is that it formed by an integral calculation. It does involve an integration here, folks. Right? We might assume that we have the above polar region, right? Suppose a polar region R forms in two-dimensional space, bounded by the curves r equals f of theta and r equal to g of theta over values of theta from alpha to beta, where f and g are continuous polar functions, there's no holes or gaps in these, over these values of theta, with g of theta being closer to the origin than that of f of theta. The area trapped within this region R, the region we have illustrated above here, right, is just going to be, now this might look a little familiar, at least some aspects of it will. It is going to be 1/2 the integral from alpha to beta for this integrand with respect to theta, where you'll notice within the integrand, we are taking the difference for the square of our two polar functions, where polar function f of theta is bigger than and comes first in the difference, right, minus the square of g of theta, right, where g of theta is less than or equal to f of theta. All right. This does look a little similar, first of all, to this formula seen above for the area of a polar rectangle, right? At least the integrand seems to look similar, and that 1/2 playing that role of a constant multiple is played in there. But from beta to alpha, right, or alpha to beta, this difference, right, being the size of this region, that is what is being used here to define our integration. Right? We are integrating over these infinite angle measurements of theta, these infinitely small angle measurements that occur from alpha to beta. All right? We'll see this develop in the proof here at the end of this notes, but before we get into the proof, let's look at a quick example. All right? If we consider an example, right, we might consider the area of the region R bounded by the polar curve r equals 1 plus the cosine theta and the polar curve r equals 1 over values of theta in the closed interval from 0 to pi over 2. Right? If we sketch these two polar curves into the two-dimensional space in which they're defined, you will have r equal to 1 define that circle centered at the origin with radius of 1. That would be this circular shape here, right, in that space, as well as this polar curve r equals 1 plus cosine theta, where r equals 1 plus cosine theta forms this shape seen here known as a cardioid. right? This, some might say, looks a little like a heart shape when turned on its side, right? And this we're interested in is the area bounded by these two polar curves, the cardioid and the circle, over values of theta in the interval from 0 to pi over 2. Now, theta equal to 0 defines the angle measurement that falls here along the positive x-axis, so it's defining this horizontal edge to this polar region. And theta equal to pi over 2 defines the location in this space occurring at positive y values. Right? Where you'll notice that edge of the polar curve really isn't an edge, it's collapsed now down to the value of a point. Right? And what we have here is this region forming over these angle measurements all the way down to this value at this point, right? From theta equal to 0, the region starts to form between these two curves all the way down until we reach this point at the value of theta equal to pi over 2. All right? How do we calculate this area? As we use the above formula. Theta and pi over 2 are going to just play the role of our bounds. F of theta is going to be the outer edge of this polar region, the edge that is furthest from the origin. All right? That's going to be given by 1 plus cosine theta. And g of theta is going to be the inner edge, the edge of this polar region that is closest to the origin. That's going to be given by the circle of radius 1. All right? If we plug those values into our formulation, all right? So I point out in this case, f of theta is 1 plus cosine theta, g of theta is equal to 1, and theta is in this interval from 0 to pi over 2. So that area is just given by this calculation here. It is happening from 0 to pi over 2, where 1 plus cosine theta is playing the role of f of theta, and the value of g of theta is played by the constant value of 1. All right? Expanding these two arguments inside the integrand, squaring the 1 plus cosine theta, produces this quantity, right? This polynomial form in terms of the cosine. 1 plus 2 cosine theta plus the cosine squared theta, minus the expansion of just 1 squared is 1, right? We just have subtracted 1, simplifies now where the plus 1 and the minus 1 cancel into just 2 cosine theta cosine squared theta. Where if I think about those antiderivative formulas, I could probably look those up in the integration tables, and in fact I do. Where if we note in the integration tables, 2 cosine theta is just 2 sine theta, and cosine squared theta simplifies the theta over 2 plus 1/4 the sine of 2 theta. Where if I now evaluate these across these bounds, notice at 0, sine of 0 is 0, so this turns into 0. 0 divided by 2 is 0. So the first two terms add up to 0, and then the sine of 2 times 0, again, the sine of 0 is also 0. So the third term results in 0 along with the first two, and this entire quantity becomes 0 when we just evaluate it at 0. So that all will 0 away, whereas at pi over 2, the sine of pi over 2 is 1. So that's 2 times 1, that's 2, plus the pi over 2, divided by 2, which is pi over 4. Plus 1/4 times the sine of 2 times pi over 2. Now, 2 times pi over 2 is just pi. The sine of pi being 0 also in value. So at pi over 2, this whole thing will 0 away. And we'll just be left with 2 plus pi over 4. All right. We do see that developing here in our notes. We do get left with 2 plus pi over 4. Now times the 1/2 simplifies to 1 plus pi over 8 units squared. That describes the exact area of this polar region. All right? This polar region that occurs between this outer polar curve, f of theta equal to 1 plus cosine theta, and this inner polar curve described by the circle g of theta equal to 1. And this region forms over values of theta from 0 to pi over 2. Right? That is what's given by this calculation. Right? And once set up, it does fall upon fundamental integral rules here. Right? The cosine antiderivative is sine, cosine squared's antiderivative is theta squared plus 1/4 sine of 2 theta. Right? That 2 just plays a constant multiple in the case of the cosine. Right? We're evaluating across these bounds is rather elementary also. Right? And simplifying to 1 plus pi over 8 is a rather fundamental calculation here, folks. Right? A rather fundamental integral calculation for what is a rather complex region of space. Right? Notice that's what polar curves and interpreting regions of space in the polar context is useful for. Right? If we try to define this region of space in terms of x and y, this calculation could be just terribly difficult, if not impossible. But because we interpret this region of space in the polar context, that calculation for area, right, that we see developed down below here, this calculation right here, is a rather fundamental calculation in terms of its antiderivative and that evaluation of it across the bounds from 0 to pi over 2. Right? Now, if we spend a moment on proof, right, here's what we might consider proving. In this proof, again, we are consider proving this area calculation given by this integration, right, which does describe the area calculation for this region of space, right, where we note here, we begin as we typically do in these formulations and these proofs, and we begin by subdividing the interval over which we're integrating into n subintervals. Right? We are integrating over an interval of angle measurement theta, right, from alpha to beta. We are integrating over this region of space from theta equal to alpha all the way up to theta equal to beta. And we're going to divide this up into these little bitty polar regions. Right? We're going to subdivide them into n polar regions by subdividing alpha to beta into n subintervals. Right? And if we subdivide from alpha to beta into n subintervals, that is going to give us the width of one of those subintervals. Right? That being given by delta theta, which is nothing more than beta minus alpha divided by n. Right? And as I had noted, what this does in turn do is subdivide our polar region. This region here gets subdivided up into n polar regions. Right? Where those n polar regions are approximately polar rectangles in shape. If I think about slicing this up in a polar coordinate system, right, from g of theta to f of theta, making these slices along angle measurements from theta equal to alpha to theta equal to beta at equal increments, right? This will slice this into these little tiny strips of polar regions, where those little tiny strips of polar regions are essentially this shape. Right? They are essentially this shape seen back here, the shape of a polar rectangle. Right? This polar rectangle seen back here. Right? Where how do we calculate the area of that polar rectangle? We rely on this formula. Right? We're down below here. Right? We will see that develop in our proof. Right? That area of just one of those little shapes is given by this calculation here, which is the area calculation for a polar rectangle happening at theta sub k being an angle measurement of theta in the kth subinterval from alpha to beta. Right? if I take 1/2 times f of theta k quantity squared minus g of theta k quantity squared, this is like finding 1/2 the outer radius squared minus the inner radius squared, r2 squared minus r1 squared. Where beta minus alpha now is not considering this entire space of theta, but is just the little subinterval of space which we know has a width of beta minus alpha divided by n, or what we have defined as delta theta. So delta theta becomes that measurement of the angle over which this polar region is forming, right? This polar rectangle is forming, right? Now, if I take this polar rectangle, all right, calculate, well, if I think about the area calculation or approximation for just the kth subinterval, sorry, folks, where was I? So if this is the calculation for just one of those kth subregions of this polar region above, we can approximate the total area by summing it up, right? All the areas in the kth subregions, starting at k equal to 1 and continuing up through the nth one, right? We would approximate that total area as the summation seen here, where we know then we can make that exact by just applying a limit as n heads to infinity to that calculation. Right? So here gives us our exact calculation for that area in terms of the limit of this Riemann summation that is occurring in the polar coordinate context, right? Where we know from the definition of a definite integral, the limit of this summation is what turns into our integration over this interval from alpha to beta, right? It happens with respect to, now delta theta is what highlights the d theta in that integral calculation, right? From our definition of the definite integral. And our integrand is what remains, the 1/2 times this quantity f of theta k sub k squared minus g of theta sub k squared, where the 1/2 becomes a constant multiple brought out in front of the integration, and in the f of theta sub k and the g of theta sub k values, the theta sub k has the k dropped as a subscript and just becomes variable theta. All right? So, folks, this is, again, the proof, right, of that formulation we developed in the above theorem. Right? We put an ender on here. Right? That is our end proof. Right? And keep in mind, what we were looking at here again was the area trapped within polar regions. Right? The area trapped within very generic polar regions, where we think of defining the polar region as we've seen here in general. Right? It is this region of space that's trapped between angle measurements of theta from alpha to beta. Right? Between polar curves f of theta and g of theta. Right? F of theta being the outer bound, the boundary on this polar region that is described being furthest from the origin. G of theta being the boundary defining this region closest to the origin. And the closest you can be to the origin in this system is 0. In fact, you will even encounter cases where g of theta is equal to 0. If g of theta was 0, that would be all the space trapped within this entire portion of what would be approximately a sector in shape. Right? But g of theta can also be defined by some other polar curve. All right? So, folks, that's another quick video here where we're looking at calculating area bounded by polar curves. All right? So, I hope you're hanging in there with these. I have one more video to give you over the calculus of polar curves where we want to look at arc length of polar curves. All right? So, I'll be back with that in another video. So I'll see you then.